Welcome back to electrochemistry. In part 6, the final part of this unit, we're going to be talking about cell potential versus free energy, that is delta G and E standard, and also the Nernst equation, so we can compare cell potential and free energy. So let's get started. So first of all, let's look at the relationship between cell potential and free energy. So that relationship is delta G standard is negative N F E. So we know that delta G is the free energy. That's how much work is done on the system or how much work is required to get the reaction to happen. And you know E0, that's the cell potential. That's how much voltage will go through a battery if you've got a battery hooked up of two random things. We have F, which is Faraday's constant, 96,500 coulombs per mole of electrons. And then we have N. Did you remember that N is number of moles? And in this case, that number of moles is going to be number of moles of electrons. Let's see if I can write that prettier. There you go. Number of moles of electrons. And remember that just for units' sake, a volt is a joule per coulomb because we might need that unit again later. So let's just start with a reaction and see if we can work this equation into it. We have magnesium plus silver nitrate makes magnesium nitrate plus silver. I'm going to go ahead and balance that because I can't stand looking at a reaction that's not balanced. So first thing I need is E0. That's the cell potential. So that you're going to get off of your reduction potential chart. And you're going to be looking at magnesium and Ag plus, not plain Ag, but Ag plus. I see that there is a half reaction that looks like this. You don't have to write this half reaction down, but that's what I'm looking at when I see the chart. And it's 0.80 volts. And then I'm looking for another one, and I see a magnesium that looks like this. Makes Mg, and when I see that, it has negative 2.37 volts. Okay, so based on the balanced equation that I had already done, this Ag is in fact Ag plus, which means this reaction is reduction, and the voltage can stay exactly like it is, 0.80 volts. But the magnesium is different. It starts as Mg0, not Mg plus 2. So this reaction is going in reverse. So this will be a positive 2.37. So the cell potential is 0.8 plus 0.237 is equal to 3.17 volts. Is that spontaneous? Yes, it is, because 3.17 volts is a positive number of volts. All right, we'll get that out of the way, and then we'll look at delta G. Erase, erase, erase. Clear, clear, clear. Oh goodness, I erased the balanced equation. That's awful. Let's fix that. Okay, so now we want delta G. And you could use products minus reactants and go and find the delta G for the products and the reactants, but here we're going to use this brand new formula because otherwise, why did we get a brand new formula if we weren't going to use it? So we have delta G is equal to negative N F E. Okay, did you notice that I left N blank? Hopefully you did. So N is the number of moles of electrons, specifically the number of moles of electrons that are transferred in this reaction. So for that, look at the charges. Mg starts as a 0 and it ends as a plus 2. Which tells me that it lost 2 electrons. Silver starts as a plus and it ends as a 0, which means it gained only 1 electron. But since there's 2 silvers, they gained 1 electron each, which is a total of 2 electrons. So I'm going to put 2 moles of electrons in that for that N. And that's it. Just calculate. Negative times 2 times 96,500 times 3.17, and you end up with negative 611,810. Okay, hopefully you know me by now, and units is something that we have to fix. We have to figure it out. So the moles of electrons are going to cancel, and I end up with a unit of coulombs times volts. And remember that a volt is a joule per coulomb, so I could have just as well said coulombs, let's see, times joules over coulombs, because that's a volt. And then the coulombs cancel. So my unit ends up being joules. Ta-da! Which is not really a very good unit for delta G. Usually delta G is in kilojoules. So there's 1,000 joules per every 1 kilojoule, which is really negative 612 kilojoules for that reaction. Is it spontaneous? Yes! And I know because delta G is negative. A negative delta G means a spontaneous reaction. So then the last thing I need to figure out is K. And I did not just give you an equation to solve for K, so I'm not going to use a brand new equation. I'm going to have to use a brand old equation. Do you remember a brand old equation that will relate delta G and K? Hopefully you're thinking in your head delta G is equal to negative RT ln K. That equilibrium is coming right back at you. So delta G we already figured out is negative 612 kilojoules is equal to negative R. Remember, R is 8.3145 joules, but we really want kilojoules, so 0.00831145. So I'm going to write kilojoules per K mole. And then T is temperature. Temperature. I don't see a temperature given, so I'm just going to go ahead and assume 298 K. Not awesome to assume temperatures, but what are you going to do? Then we have ln K, and K is what we're solving for. So I'll have negative 612, and I'll divide it by these two numbers. So divide by 0.008315 and divide by 298, and I end up with ln K is equal to, I don't even know, 247? Did you guys get 247? Okay, so then we need to find what K is actually equal to. So I'll take e to both sides, so I'll end up with K is equal to e to the 247th power. If you type that in your calculator will probably tell you overflow, this will not work, overflow, because to an exponent of 247, that's a ridiculously high exponent. So what I'm going to say for my K, I'm going to erase all this to get it out of the way. I'm going to say K is equal to e to the 247th power. Ta-da! Okay, let's look at another one. So just a second ago, we were trying to find K based on delta G, because I said I didn't give you a fancy formula to find K based on anything else. So now we're going to get a formula to find K based on something else. And we're going to use the Nernst equation to do that. Wilhelm Nernst found that cell potential or voltage depends on the concentration of electrolytic solutions. So think Le Chatelier's principle. If I increase the reactants, the reaction is going to go forward to the products, or if I were to increase the products, it's going to go backwards to the reactants, or if I were to decrease the products, it's going to go and remake those, or if I were to decrease the reactants, it's going to go forward and make those. So let's just see it in person. Given 2Al plus 3Mn plus 2 makes 2Al plus 3 plus 3Mn. Let's predict whether E is larger or smaller than E. Notice that this is my non-standard E, so this is when the concentration can be anything, and that this is my standard E, which means the concentrations are all 1. So assuming that we are starting at 1, how is it going to change when my concentrations are no longer 1? So for example, in part A, I have Al plus 3 is 2.0. and I have Mn plus 2 is 1.0. So notice that I have increased the product side, and if you increase the product side, the reaction is going to say, whoa, too much, and it's going to go towards the reactant side, so it's going to shift left. But the question is not shift left, shift right, it's whether E is larger or smaller than E. So if the reaction is going to shift left, it's going towards the reactants, which means it's less spontaneous, and an E that is less spontaneous is something that is more negative. So E will be smaller than E, or E standard. Let's look at another one. What if, instead of the 1 and the 2, we had Al plus 3 was the 1, and the Mn plus 2 was the 3. So now we've increased the reactants, and the reaction's going to say way too many reactants and try to get rid of those reactants by forming more products. So it's going to shift right. And if it's going to shift right, it's going to make more products. It's going to become more spontaneous, so that E is larger than E standard. Now this is the actual Nernst equation. E is equal to E standard minus 0.0592 over N. Remember, N is the number of moles of electrons times the log of Q. Remember that Q is the reaction quotient. So looking back at that last problem when I had to predict whether E not standard is smaller or larger than E standard, so now I'm going to actually calculate and see if those predictions were correct. So first thing we need is E standard. You're looking on your chart for the aluminum and the manganese. Notice that the manganese is being reduced, so it gets the number off the chart exactly as written. The aluminum is being oxidized, so it gets the number off the chart reverse from what's written. And if you pause the video, find those numbers and calculate, come back to me in just a second. Pause your video now. Alright, hopefully you came up with E standard for this reaction is 0.48 volts. That is switching or reversing the number for aluminum and then taking the number for manganese exactly as is. So this is going to be our standard that we're comparing the E not standard to. So I have E is equal to E standard, that's 0.48 volts, minus 0.0592 over N. N is the number of moles of electrons transferred. Notice that Al goes from 0 to plus 3, so that's 3 electrons transferred, but there are 2 aluminums that transfer 3 electrons each. That's a total of 6. If you look at the manganese, there's 3 manganese that transfer 2 electrons each, which is also a total of 6. So there's 6 electrons transferred. And then we have the log of Q. Remember that Q is the reaction quotient. That's products divided by reactants. And so our Al is 2.0, our Mn is 1.0. So our product for aluminum is 2 squared. You see that there's a square there. And then Mn is 1 cubed. Notice I didn't bother with this Mn or that Al because those are solids. Those 0 charges mean solid, and solid does not get included in any kind of equilibrium anything. And so now I'm just going to solve. I'll take 2 squared is 4 divided by 1 cubed, which is 1. So then the log of 4 times 0.0592 over 6, and then subtract that from 0.48. And I'll let you pause right now and calculate that on your own and come back to me and see if you got something. And I got 0.474 volts. And 474 is smaller than 0.48, which means that that number is exactly as we predicted, smaller than E standard. Let's do the same thing for the other concentrations. E is equal to 0.48 volts minus 0.0592 over 6 moles of electrons times the log of, and so now this time we'll have the Al as 1 and the Mn as 3, so we'll have 1 squared over 3 cubed. Let's make that a cube. So that's 1 divided by 27, take the log, and go ahead and solve. And I ended up with 0.494, which is higher than your E0, just as we predicted. So it kind of goes along with Le Chatelier's principle. Take note here, though, that the College Board does not want you to use Le Chatelier's principle as an argument, because that's for a reaction at equilibrium, and by making these non-standard concentrations, we are no longer at equilibrium, so don't actually use the words Le Chatelier's principle, just think Le Chatelier's principle without writing it down. Alright, let's do some Nernst equation again. We're going to diagram the following: a zinc-silver voltaic cell. Remember, voltaic, also known as galvanic, is the one that is a battery. It's the one that is spontaneous. It has usually some sort of voltmeter through the center. It has a salt bridge, 2 pieces of metal, 2 aqueous solutions. Alright, so now we got zinc and silver. Check out on your reduction potential chart who's higher, and hopefully you're coming up with silver is higher, so silver is the one that's going to be reduced. So I'll put Ag there and Ag plus here and call this reduction. And the cathode. Since Zn is lower, then Zn is the one that's going to be oxidized, so I'll make this the zinc metal. This the zinc ion in solution, this the oxidation, which is also called the anode. And the electrons always travel across the wire from the anode to the cathode. They always travel from oxidation, which is loss of electrons, to reduction, which is gain of electrons. And also notice that, just to mess you up, I put oxidation on the right-hand side instead of the left-hand side, because those really can be flipped back and forth whichever way you want to do it. And let me go ahead and label this a salt bridge. Okay, so that's my diagram of my zinc-silver voltaic cell. Now, it also wants me to find the E0, so I'm going to look on my chart. And I end up finding that E0, since silver is higher, silver stays exactly like it is. It's a positive 0.8. Since zinc is lower, zinc gets flipped, so it becomes a positive 0.76. It used to be a negative 0.76, which gives me a total of 1.56 volts for a standard cell, assuming we've got 1 molar Ag plus and 1 molar Zn plus 2. All right. Now we ended up with 1.56 volts. Let me go ahead and write this balanced equation. I feel like a balanced equation could always help. We have Zn is where it starts, and Ag plus is where it starts. On the other side we'll have Zn plus 2, and Ag0. We'll need 2 of those silvers to make the whole thing balanced. So now we're going to calculate the cell voltage, or E, of the zinc-silver voltaic cell. When I've changed the concentrations, it's no longer standard. Now it's a 0.1 molar zinc and a 10 molar silver. Okay, E is equal to E0, 1.56 volts, minus 0.0592 over N. N is the total number of moles of electrons transferred. So the zinc went from 0 to plus 2, that's 2 electrons, or 2 silvers went from plus to 0, which is also 2 electrons, times the log of Q. Q is products divided by reactants. So we have not right there, 0.1 for this Zn plus 2, and 10 for the Ag plus, and completely ignore solid silver and solid zinc. So we have 0.1 on the top and 10 on the bottom, and the 10 is squared because the silver has a 2 in front of it. So 0.1 divided by 10 squared, or divided by 100, and now we're going to solve, take the log. We end up with 1.56 volts minus a negative 0.088 is equal to 1.65 volts. Last thing on this problem, let's make sure that makes sense. Since we're increasing the reactant side, the reaction should say way too many reactants and shift towards the products, which means the E0 should get larger. It's becoming more spontaneous, and it does. From 1.56 to 1.65, the voltage increases. Now let's connect this Nernst equation to equilibrium. So instead of the Q, we're looking at K. So remember, at equilibrium, the delta G is 0, and also the E is 0, for the same reason. At equilibrium, we are just on the verge of spontaneous, non-spontaneous. So it's not negative, it's not positive, it's got to be in the middle, which is 0. So I take my original Nernst equation, and I change my E to 0. Everything else stays the same. Then I'm going to add this term to both sides, and so then essentially that term flips to the other side, and I end up with a new formula. E0 is 0.0592 over n log K, because at equilibrium, the Q changes to K. Let's use that equation. Calculate K for the reaction of zinc and silver nitrate. This should be a familiar reaction at this point. We've done this reaction several times. And let me grab my really cool, really new equation. E0 is equal to 0.0592 over n log K. So that is, oh, E0, we already figured that out a minute ago. That was 1.56. Is equal to 0.0592 over 2, because again, zinc is going from 0 to plus 2. Log K. So we end up with log K is equal to 52.7. If you take 10 to the power of 52.7, K is 5.04 times 10 to the 52nd power. Woohoo! That is a spontaneous reaction with a really large K. All right, let's keep going. I have another equation with aluminum and aluminum ion and tin 2 and tin metal. So first thing I've got is to find E0. You're just going to kind of do this on your own as a reference, so you'll know later on whether you're going to go up or down. And so notice that aluminum is the one being oxidized, so you're going to take that number off the chart and flip it. And tin is the one being reduced, so you're going to take that number off the chart and keep it the same. Also, make sure you're looking at tin 2 and not tin 4. There is a tin 4 on there as well. You want tin 2 to 0, not tin 4 to tin 2. So if you calculate your E0, hopefully you get what I got, which is 1.52 volts. If you didn't get that, pause your video now. Try to make sure you can figure out how I got 1.52 volts. All right, so now we're going to determine E. So we need a reaction. We have Al as my first thing being oxidized, and Sn plus 2 as my first thing being reduced. On the other side of the arrow, we have Al plus 3 and Sn. And so now I need to balance it. I've got one aluminum on each side, one tin on each side, but the charges don't work. So I need 6 pluses and 6 pluses to make the charges balance, and then 3 tins and 2 aluminums to make the atoms balance. So now I have a balanced equation. Let's look at the concentrations. The Al plus 3 is 10 to the negative 5. 1 times 10 to the negative 5. And the Sn plus 2 is just 1.0. That makes life simple. So my equation is E is equal to E0, 1.52 minus 0.0592 over N. N is the total number of electrons transferred. Since we have 2 aluminums turning into 2 Al plus 3s, that's 6 moles of electrons transferred. Then we have log, and now I'm going to plug in the numbers. That's 1 times 10 to the negative 5 squared over 1 cubed. And then we will solve. 1.52 minus negative 0.0987. And we have 1.62 volts. All right, so there is my E, my non-standard E. Now it's time for you to try one on your own. Go ahead and pause the video now. Make sure you get your equation balanced, and you're going to determine E standard and then E not standard. Pause your video now. All right, hopefully you paused, took a break, and figured out how to balance this equation. We'll always start with a balanced equation. That's the easiest thing to do. Then we're going to look on our reduction potential chart and find out the E0. Thankfully, I've already done this reaction earlier in the notes, and so I got 0.48 volts. Now I'm going to determine the E given the following concentrations. So E is equal to E0, that's 0.48 volts, minus 0.0592 over N. N is the total number of moles of electrons transferred. That's going to be 6, because you have 3 Mn plus 2, so there's a total of 6 plus, going to 0. Times the log of Q, and Q is products divided by reactants raised to the power of their coefficients. So Mn plus 2 is 2.5, and Al plus 3 is 0.5, and manganese is a solid, so it doesn't count, and aluminum is a solid, so it doesn't count. So I end up with 0.5 squared divided by 2.5 cubed, and then we're going to solve that, and I have 0.48 minus negative 0.018, which is 0.498 volts. Ta-da! There you have E0. All right, one last problem. A cell, originally under standard conditions and functioning according to the equation below, runs until the zinc is 1.14. Find the gold. Okay, this is going to be tricky. Originally, as in initially, it was under standard conditions. Initially, we had 1.0 of the Au plus 3 and 1.0 of the Zn plus 2, and I don't care about solids. But then it changed by some amount so that at equilibrium, the Zn plus 2 was 1.14. So what must the change have been? Well, if it went from 1.0 to 1.14, the change was obviously plus 0.14. And if the change for zinc is 0.14, then the change for gold, notice that there's a 3 and a 2. So we're going to multiply by 2, divide by 3. If that totally confuses you, look at it a factor label, 0.14 Zn plus 2. For every 3 Zns, there are 2 golds. So that's why you multiply by 2, divide by 3. I end up with 0.093. Now, since that is a reactant, then that's going to be a negative, just like products are positive. So 1 minus 0.093 is 0.907. And that's it. That's our answer. They're asking us for the concentration of Au plus 3, and it is 0.907. So at the very end there, we threw in an icebox problem, just so you didn't forget that icebox problems still exist. And there you go. That's electrochemistry. I hope you had a lot of fun. We'll see you at the AP test.